today so that you all are familiar with how to solve problems on the Laurent series. Okay. Laurent series problems are extremely important, especially from the point of view of net exam. A lot of questions from the Laurent series actually comes in the net exam. So in today's class, we'll be doing basically that. Okay, so we'll be looking at some of how to compute the Laurent series for a given function about any point or over any range of values. Okay. Please let me know when you are able to see my screen. Is my screen visible?
Yes, sir.
All right. So this is basically where we had stopped in the previous class, right? So we proved that the Laurent series, okay, the Laurent series actually converges. And what is the Laurent series? This is the Laurent series. Okay, this is the Laurent series. This is the Laurent series, and this Laurent series, it converges. We proved that in the previous class. Okay, it was quite a long proof, but the result is very satisfactory. So now we will do some problems, but before we do that, I'll just give you, I'll just show you what really this is all about. Okay, so we know about the Taylor series. So let's say okay, what is the Taylor series? So suppose I have a function f of z which is analytic. Okay, suppose I have a function, we have f of z which is analytic. So what does the Taylor series say? It says that this function f of z can be written as some constant, right? Some constant value plus about some point. I could expand this about some point. So some other coefficient into z minus z naught. Okay, about z equals z naught. Okay, about some point z equals z naught. Then we have a2 z minus z naught squared, a3 z minus z naught cube, and so on. So this is how a Lorentz, this is how a Taylor series expansion, this is how it looks like. Now you can see here, this has got only all the positive powers of z minus z naught, right? So it consists only of the positive powers of z minus z naught. Okay, so this is what it contains. It contains only the positive powers of z minus z naught. So now, what if? But this is only if the function is analytic. Okay, if the function is analytic. But suppose the function is not analytic about some point z naught. So in that case, what happens? In that case, we can no longer write this function as a Taylor series expansion. Rather, we should look for another expansion. And what is that expansion? That expansion will contain not only the positive powers, it will also contain the negative powers. Okay, it will also contain the negative powers. That means, so we will have, just like we had this one, so we will have something like this. We will have something like this. The difference is we will now have negative powers. Here the power is plus 1. Now here the power is minus 1. Okay. So likewise, in a similar way, just like we had a2, okay, z minus z naught whole squared, we will also have a minus 2 z minus z naught to the power minus 2. So we are basically talking about negative powers here. So a minus 2 z minus z naught to the power minus 2. Okay. In a similar way, we will have a minus 3 z minus z naught to the power minus 3. This one extended towards positive infinity. This, I mean, it extends this side. This is going to extend in the other direction. Okay, so this Taylor series had a starting point. The starting point was the constant coefficient, but this series it extends both ways. Okay, it was like the Taylor series, but it extended both ways. So this is your Laurent series. This is your Laurent series, and we could say that this function f of z, this function f of z, can be written as a Laurent series about z equals z naught, where z naught is a singularity of this function. So now this negative powers, you could also write it like this, right? This negative powers, you could write it something as this. So dot dot dot, we have plus a minus 3, a minus 3 coefficient, and divided by z minus z naught cube. This is the same term. Okay, this is the same term, very same term as we wrote in the previous case. So this is one. Then the next one will be a minus 2, and we have z minus z naught squared. Then we have a minus 1, and simply z minus z naught. Then we have a naught, and so on. The rest of this, oops, the rest of this just follows from the Taylor series. Okay, so in general we could just write this as this, just like how in this case. Okay, in this case we could just simply write this as a summation, right? We could write this as summation. We place a summation, and inside the summation we place a generic term like this. So we say a and z minus z naught to the power n, and this n goes from 0 all the way till infinity, right? So this is what we have written it. So we can write a similar kind of a summation here. Okay, we could write a similar kind of a summation in this case also. The only difference, what will be the difference? The difference is here the values of n, the values of n will not start from 0, rather the values of n is going to start from minus infinity all the way till and extend all the way till plus infinity. So that's the difference. So this is the form of the Laurent series. So remember, Laurent series will always have, we will be able to get a Laurent series expansion in case the function is having some kind of a singularity. In case the function is not analytic at some point, then we can have a Laurent series expansion. All right, is that clear? If it does, if the function is analytic everywhere, you can just go for a Taylor series expansion. Okay, so in a way this Laurent series, okay, in a way, as you can see from here, this Laurent series is a generalization of the Taylor series. Taylor series is a special case of the Laurent series. Okay, so Laurent series takes care of the scenario where the function need not be is not analytic about z equals z naught. In fact, Taylor series is also a kind of a Laurent series only. Is that clear?
Yes, sir.
All right, so now let's do some problems, okay? Because unless and until you do some problems, then it is not going to be clear. So let me first, let's do these problems. First, we will do three problems. Okay, I'll first do this one. Then this is a little bit involved. Even if it looks simple, but this problem is involved because of the boundary that we have here. And I'll do this one. So these three problems we'll do. Okay. So problem number 1. Okay, question number 1 is this. We expand f of z, okay, which is equal to 1 by z minus 1 into z minus 2 as a Laurent series over this range of values of z, okay. First things first, how do we go about solving these problems? We can use, in such problems, whenever you are asked problems like this, we can use two expansions, okay. So we can use two geometric series expansions, two very useful results that you are already familiar with. So in such problems, in such problems, the following results for geometric series. And what are those results? There are two results that we need to keep in mind. The first result is 1 divided by 1 minus q. 1 divided by 1 minus q. Does anybody remember what is this series? What is the summation? This is basically a geometric series, okay? So what is the geometric series? It is simply 1 plus q plus q squared plus q cube, okay? Essentially this is, if you write this as a summation, so this is equal to summation of q to the power n, summation of q to the power n, where n goes from 0 all the way till infinity. But this is under the condition, there is a condition. What is the condition? The condition is that the modulus, this is valid for both real as well as complex numbers. The condition is that the modulus of z, okay, it must be less than 1. That's the condition. Okay, so this summation is valid only if the modulus of z is less of modulus of q is less than 1. Only then it is valid, okay. For all q, for all q. So q could be real, it could be imaginary, it could be complex, okay. So this is the geometric series, one result. Another result is 1 by 1 plus q. Does anybody remember? 1 by 1 plus q. What happens to the result? 1 by 1 plus q. What will be this result? Anyone?
Oh, 1 minus q
Okay.
plus q
Oh,
square
sorry,
minus
just one second, just one second, one second. I made a small mistake here. The mistake is it will go on. It's a series, right? So it should go on and on. Let me just add that. Just give me a second. It should be plus dot dot dot. Okay, same thing holds good for here also. So same thing. Okay, Mafidul, was it Mafidul? Yeah, you can continue now. So this will be equal to
1 minus q
1 minus q
plus q square
plus
minus
q. Okay, great. So that means there is going to be alternate plus and minus sign, right? There is going to be an alternate plus and minus sign. Okay, so it will not be plus everywhere, it will be alternate plus and minus signs everywhere. Okay, how will this change? How will this change? How do you get this alternate plus and minus sign? All we need to do is very simple, just put minus 1 whole to the power n. minus 1 to the power n, that is going to take care of this alternate plus and minus sign. N equals to 0, this will be plus, n equal to 1, it will be minus, n equal to 2, it will be plus again. So that's how it's going to be. Okay. In both the cases, this is important. Okay. This is extremely important. This is going to be the key for solving this. In both the cases, modulus of q, it must be less than 1. Okay. So in such problems, when we use this following result. Okay. Then another useful result that we can use. Okay, another useful result, what is known as the method of partial fractions. It's not a result, it's a method. Another useful tool in such problems, it's known as the method of partial fractions. Method of it's known as the method of partial fractions. Okay, what is the method of partial fractions? Method of partial fractions, it basically says something like this. You could have something like this. Okay, so let's say I have in the denominator we have z minus a and z minus b. Let's say in the denominator we have z minus a and z minus b, and here in the numerator we have, let's say, uh, p of z. Okay, so if f of z is written is can be written like this. If f of z is written like this, where uh, p of z is a linear function, where p of z is a linear function of z. What is the meaning of linear function? Linear function means it's a polynomial with degree 1. Okay, so that is, this p of z is written as let's say mz plus n. Okay, so you could write it like this. Okay, so it's basically a linear function of z. The rule is basically the partial fractions you can use if the degree of the, if the numerator and denominator, if the both numerator and denominator, they can be written as polynomials, but the degree of the numerator is 1 less than the degree of the denominator, then you can use the partial fractions. Okay, I'll mention that. Okay, then then f of z can be written as f of z can be written as f of z equals, this is the first factor, right? So this is the first factor. First factor is z minus a. That's the first factor. Z minus a is the first factor, and the second factor is z minus b. So what we can do is we could write this in terms of two fractions, one containing the first factor, another containing the second factor, z minus a and z minus b. And we are able to do that provided in the numerator. Okay, in the numerator, so this also we are writing as two different fractions, that's why it's known as the partial fractions. In the numerator we have some constant a, and in the denominator and in the second one, in the numerator, we have some constant b. Okay, where this a and b are to be determined. Where a and b are to be are to be determined. Okay. I'll just mention it in general. When can you use this method? In general, in general, this method, this method is applicable, when f of z is written as in terms of u of z and v of z. If f of z is written as a you know a quotient of two functions u of z and v of z, where u and v are two polynomials such that degree of u of z, because it's a polynomial, it will have a degree of u of z is equal to degree of v of z, it is less than the degree of the denominator by 1. So if the denominator has got a degree 5, the numerator should have a degree of 4. Then only it will work. Okay, so likewise, if the denominator has got a degree of 2, the numerator should have a degree of 1. Okay, so like in this case, you see, what is the denominator? What is the degree of the denominator? So we have a product of two terms. Both of them are linear, product of two linear terms. Product of two linear terms will be quadratic. So because we'll get a z square, that's the highest power, right? So z square is the highest power, so its degree is 2. So that means P of Z, its degree must be 2 minus 1. Its degree must be 1. That means it must be linear. That's why it's a linear function. Okay. So these kind of problems, you can use, these two tools. You can use this result for a geometric series, and you can use this method of partial fractions. Both of these we can use to actually solve the problem that is given here very easily. Okay. So let's do that. So this is the problem. Okay, so now first things first, we need to figure out what does this mean. Okay, so first we need to figure out what is the meaning of this one. Okay, that means what is the domain, okay, that we are talking about. So for doing this, what you do is you just first draw this. Okay, now you remember, right? Whenever I say modulus z, okay, so recall this one. Recall this, that is, if I say z minus z naught, if I say z minus z naught is equal to r, what does this imply? It implies a circle of radius r centered at z naught, right? So this is what it implies. It's a circle of radius r which is centered at z naught, right? So let me just draw this. So we will have so let's say this is a complex plane. This is a complex plane, and this is z naught. Okay, this is z naught. So what is z minus z naught equal r? Z minus z naught equal to r is basically a circle of radius r which is centered at z naught. Okay, the circle of radius r which is centered at z naught. So basically this is what we're talking about. Okay, so we're talking about a circle such as this one. Okay, and the radius of the circle, the radius of the circle is r. So this is what is meant. So this circle that we have over here, this is your z minus z naught equals r. Okay, remember this. Okay, so this is going to help you actually in problems like this. Now if I have something like this, instead of this, let's say if I have something like this, I have z minus z naught. What if this is less than r? So in that case, what happens? Z minus z naught is less than r. So in that case, what happens? Okay, so in that case also we are going, this will also involve a circle. Okay, in this case will also involve a circle. The difference will be, now we are not talking about the circumference of the circle, we are talking about the area which is covered by the circle. Okay, so there's a difference between the two. So let's say this again, let's say this is your z naught. Okay, this is our z naught, and once again we draw the circle. Once again we draw the circle. Okay, so this is a circle. Give me a second. Let's do. Okay, this is a circle. So now its radius is r. Okay, this one's radius is capital R. This is the radius of the circle. So what is the meaning of z minus z naught less than r? Z minus z naught, this less than sign, okay? This less than sign that we have over here, this less than sign indicates that we are talking about the points which are inside this disk. Let me be a little bit more clear about this, okay? For that, let me just zoom in a little bit. Okay, because this is less than r, right? It says it is less than r. That means it does not include. It does not include this circumference. Okay, it does not include the circumference. So essentially, we are talking about a circle which is slightly inside. Okay, so we are talking about a circle which is slightly inside. That means we are not interested in the circumference of the circle. That is this circumference. We are not interested. So it is no longer about the circumference of this circle anymore. Whereas if it was equal to r, then we were interested in the circumference of the circle. But now we are not interested in the circumference of the circle. We are interested in the points which lie completely inside this. Okay. So this is what we mean. We mean all the points which are lying inside. Okay. So these are the points that we are talking about. So these points which lie inside. Okay, so the points which exclude this circumference, that's what we are talking about here. The points which exclude the circumference, that is all these points. This is Z minus Z naught less than R. Okay, is that clear to everyone? All of you, are you clear with this?
Yes, sir.
Okay.
Sir.
Last case is, what if we have Z minus Z naught greater than R? So in that case, what happens? Z minus Z naught modulus Z minus Z naught is greater than R. So here what will happen? Okay, so here also same as before, we will assume that this is our Z naught. Okay, and we will just draw a circle. We'll draw a circle who's centered over here, slightly smaller. Okay. Okay, so we have drawn the circle here, but now again, just like in the previous case, here it is, there is no equality, right? Here it is equal. Sorry, here also there is no equality. Here also there is no equality. So since there is no equality, that means here also we are not interested in the circumference. Okay, so here also we are not interested in the circumference of the circle. Okay, so we are not interested in the circumference of the circle, but what are we interested in? We are interested in the region which is outside the circle, that we are interested in. Okay, the region which is just outside the circle. So let me make a slightly bigger circle here. We are interested in this region which is outside the circle. So this is the region that we are interested in, this region. This is your Z minus Z naught greater than R. Okay, so this is the region. So that's the difference. Okay. What if it was Z minus Z naught less than equal to R? Then what will happen? What if it was Z minus Z naught less than equal R? What will happen? Anyone? Anybody? What if it was Z minus Z naught less than or equal to R? Z minus Z naught less than or equal to R. In that case, what are we talking about? What about Z minus Z naught greater than or equal to R? So in this case also, what are we talking about? Any idea? Anybody? Anyone? Any suggestions? What could happen? Am I audible? Yeah, I am audible. Yeah. Mehtab, what do you think will happen here? Mehtab, can you hear me? Mafidul, Mafidul, can you hear me?
Sir, actually, the reason will touch
Yes,
the
that's it.
circumference.
That's it. That's it. That's the only thing. Now the circumference also will be included here. That's all. Like I said, no, whenever there is equality, the circumference. Here only equality. That means only the circumference. It's the locus of points which lie on the circumference. Less than means all the points which lie inside and not on the circumference. If it is less than equal to, then it will be all the points inside as well as on the circumference. So it will include everything. So here also same thing. Okay, all the points which are outside as well as inclusive of the circumference. Here inside and inclusive. Okay, so this is points inside and exclusive of the circumference. Points inside and exclusive of the circumference. And here this will be points outside and also exclusive of the circumference. Okay, so here it will be inclusive of the circumference. Fine. Okay, the last thing that I would like to talk about here is this. What about this scenario? What about this scenario? There is modulus z minus z naught, modulus z minus z naught is less than r1, r2. What do you think will happen here? Modulus z minus z naught is less than less r1 less than z minus z naught less than r2. What do you think will happen here? This is a complex plane. So z naught first, let us locate z naught. Z naught is this one. This point is your z naught. So here there are two radii. One is an inner radius, another one is outer radius. Okay. So let me grab my compass. So here we need to deal with two different radii. Okay. One is the inner radius, another one is the outer radius. First, the inner radius. First, the inner radius, that is R1. R1 is the inner radius. Okay, so this is the inner radius. Okay, and this is the outer radius. So we are interested in first the inner radius. So let me just go ahead and draw this inner radius. Circle with the inner radius R1 and another circle with the outer radius R2. Okay, so this is what we have. So this is your radius R1. This is your inner radius R1 and this is your outer radius R2. So this is R1 and this is R2. So now again, in this case, there is no equality here. There is only less than, okay? There is only less than. There is no equality sign here. So we are not really interested in what happens on the circumference. We're not at all interested in what happens on the circumference. So let me just make this go away like this. Not interested again what happens on the circumference of the outer circle. Okay, but it says that this is z minus z naught, r1 less than z minus z naught. What is this one? We can write it like this, right? So we have, this can be written as, this is written as, we could write it in this way: z minus z naught, z minus z naught is greater than r1, is greater than r1, and z minus z naught, z minus z naught is less than r2, right? I could write it like this part and this part. Okay, I could just split this up and write it like this. And we already know that what happens in these two cases. This is the first case. Okay, this is case number one, this is case one, and let's say this is case two, this is case 2. Okay, so here you see z minus z naught, z minus z naught is greater than some radius, right? Z minus z naught is greater than some radius. You can see here z minus z naught is greater than some radius. That means this is your case 2, that is case 2. And here we can see z minus z naught is less than r, z minus z naught is less than some radius. This is your case 1. This is case 1. Okay, so case 1, what happens? Case 1, the inner region, and case 2, what happens? The outer region. So all the points which are, because it is case 2, case 2 means outer points, case 1 means inner points. Okay, so essentially what we're looking for is, we're looking for points which are outside R1. We're looking for points which are outside R1 but which are inside R2. Points which are outside R1, points which are outside of R1 but inside of R2. So these are the points that we are looking for. So points which are outside of R1. So what are the points which are outside of R1? Points which are outside of R1. Outside of R1, this is R1. So these are the points which are outside of R1. That means we are looking for all the points which are outside this one. Okay, points which are outside of R1, but points which are inside of R2. This is R2, so points which are inside are these points somewhere over here. So these are the points that we're interested in. So essentially, we are looking for these points, the points which are outside R1 but inside R2. That means all the points which lie inside this region, and this is known as an annulus. Okay, this is known as an annulus. So all the points which lie inside this annular region. So those are the points that we are interested in. So all the points which are lying inside this annular region. So that's what we are talking about. Is that clear to everyone?
Yes,
Is that clear? So points inside the annular region. Okay, so this is known as the annulus. This is R1 less than mod Z minus Z naught less than R2. Annulus. Okay. If it is R1 less than equals z minus z naught less than equals r2, then it will include both the circumference. If it was r1 less than equal to z minus z naught but less than, first is less than equal to then less than, then it will include only the inner circumference but not the outer circumference, and so on. So we have these various different cases, okay, that we can talk about. All right. So just by looking at this one, you can tell what kind of a region that we are considering. So now coming back to this problem. So what kind of region are we considering here? What kind of a region are we considering?
Annulus regions.
It's an annulus region. What is the inner radius?
One.
One. Yes. So 1 less than z less than 2. Okay. So this is basically an annulus. Annulus with inner radius inner radius 1 and outer radius 2. Where is it centered? Where is the center of this annulus? Where is the center of this annulus?
0.
0. Z not equals 0. So whenever you're in doubt, just remember this one. Just compare it with this formula. R1 less than Z minus Z naught less than R2. Just compare it. Okay. So this inner radius is R1 and outer radius is R2, and Z minus Z naught. There is no Z naught here. That means Z naught must be equal to 0. The center is 0. Is that clear?
Yes.
Okay, so now, so it means, let me just quickly draw this here. So this is what we're talking about. So you're talking about, this is a complex plane. Okay. Inner radius is 1, inner radius is 1 and outer radius is 2. So we have the inner radius, which is 1. Okay. And then we have the outer radius, which is 2. This is the outer radius, which is equal to 2. Okay, so this is the annular region. Basically, this region is what we are interested in. Okay. Now, is there less than or less than equal to? There is less than sign, right? There is less than sign. If there is a less than sign, then that means it does not include. It does not include your. It does not include your this one radius r1. Okay, it does not include r1. Okay, so what that means for us is this. It does not include r1. So r1 is somewhere over here. Zoom in a little bit. No. Okay, leave it. What is R1? R1 is so inner radius. Inner radius is 1. So point 1 will be somewhere over here. Point 1 is somewhere over here. this is 1, and outer radius, it does not include the outer radius also, outer circumference also. So the outer radius, the point 2 will be somewhere over here. Okay, so this will be 1, this point is 1, and this point is 2. And you can see here from the example in this one, in this function, z equals 1 and z equals to 2 both are singularities. Okay, f of z is not analytic at z equals 1 and z equals 2, at z not equals 1 and z not equals 2. So that's why these 2 points are outside, they are not included. That's the reason why we have less than and less than. We are not including these 2 points. Okay, in the region in which we are considering, we are not including these 2 points. So that's the reason why we have this one. Is that clear? Okay, so now let's apply the partial fractions. Okay, applying partial fractions. Applying partial fractions. Okay, so what applying partial fractions? What do we have? What is the law of partial fractions? What's the method of partial fractions? What we need to do? Okay, just let me just correct this a little bit, such that it's not equal to, it is less than equal to. Okay, at least it must be equal to the degree of the denominator minus 1. Okay, at least it must be equal to this. Okay, so now let's go back to this problem. Okay, so here f of z is equal to, in the numerator we have 1, denominator what do we have? Open this up, we have z square, then minus twice z minus z will give us minus 3z, right, plus 2. So this is what we have in the denominator. Now you compare it with this one, it should be in this form. It should be u of z by v of z, where both of them are polynomials. So this is what we have in the numerator. This is your u of z, and what we have in the denominator, that is your v of z. So here, what is the degree? What is the degree of u? The degree of u is 2. It's quadratic. And what is the degree? Degree of v. The denominator. The degree of the denominator is v. And what is the degree of the numerator? The degree of the numerator is 0. Is the condition satisfied? The condition is degree of u, it must be less than equal to degree of v. Degree of u must be less than equal to degree of v. So 0 is less than 2. So condition is satisfied. So we can apply the partial fractions here. Is this understood?
Yeah.
Okay. So what is partial fractions? So we can basically write this. Okay. Forget about what is there in the numerator. Just look at what the factors in the denominator. We could just write this as something divided by first factor plus something else divided by the other factor. We could go ahead and we could do that. So let's do that. So let this 1 by z minus 1, z minus 2, 1 by z minus 1 divided by z minus 2, let this be equal to a divided by z minus 1, a divided by z minus 1 plus b divided by z minus 2. Now just add both of these, and when you add both of these, so what do we have? In the denominator we have z minus 1 and z minus 2. So as a result of this denominator and this denominator has become the same, and what will we have here is a times z minus 2 plus b times z minus 1. Tell me what this becomes. The numerator, what does the numerator become? Z minus
Minus Z
1,
minus 2.
Z minus 2. Yeah. So let's take the Z common, okay? So there's a AZ and there's a BZ. So A plus B, okay? A plus B Z. And then what is this left? There's a minus twice A and minus B. So minus, okay, I take minus common, twice A plus B. This is what else we have, right? Is that correct? Please check if this is correct. Is that okay, everyone? Are you satisfied?
Yes, sir.
Okay. So this is equal to, so effectively what you're saying is this is equal to this. Okay. So now if you compare this, you could just cancel out, right? We could just cancel out this one. This and this we could just cancel out. And this gives us, this implies that A plus B Z, A plus B Z minus twice A plus B is equal to 1, which can also be written as 0 Z plus 1, right? We could do that. So now if you compare the coefficients, okay, if you compare the coefficients, this coefficient, it must be equal to 0, and this coefficient, including the minus sign, it must be equal to 1. Okay, so this gives us two equations. Okay, the two equations are A plus B equals 0. This is one equation. There are two unknowns, so to solve two unknowns we need two equations, and the other one is that twice A plus B is equal to, there's a minus sign, we'll take the minus sign here, is equal to minus 1. Now please solve this and tell me what is A and what is B. Please solve this. Tell me what is A and what is B.
So A equal to minus 1 and B equal to 1.
A equals minus 1 and B equals to 1. Very good. A equals minus 1 and B is equal to 1. So hence we have this. Originally, what did we assume? We assumed that f of z is this, right? We assumed that f of z is equal to this one. This is what we had assumed, right? And so A is equal to minus 1, A equals minus 1, and B equals 1. Okay, so this implies this is a function that we're talking about. This original function f of z, it can be written as 1 by z minus 2 minus 1 by z minus 1. Is that clear?
Yes, sir.
I'm writing it in detail like this, but this you can do it like just maybe in 1 or 2 steps itself. You can do it. Okay. So let's call this equation number 1. Okay. Call this equation number 1. Now we'll have to evaluate both of these. Okay. One by one. So first, let us consider 1 by z minus 2. Let's consider that one. Okay. First, consider this one. So 1 divided by z minus 2. Let's just consider this one. What is it equal to? So, okay, how do we go about doing this? This is the place where we can use these geometric series. Okay, this is the place where we can use this geometric series. So either this expansion or this expansion. Under what condition? The condition is that modulus of q must be less than 1. The modulus of q must be less than 1. Okay. All right. So now how do we obtain this? Then we go back to this condition. Okay. We go back to this condition. This condition for the domain. Okay. We can go back to this one. We go back to this condition. So here, let's split this up. We don't need this part. Okay. We don't need this part. So modulus z is less than 2. We'll take this part only. Modulus z is less than 2. What does this imply? It implies if I divide this throughout by 2, modulus 2, this will be less than 1, right? Okay, this will be less than 1. So I might as well take the whole thing as modulus. Okay, is that clear? Is that clear to everyone?
Yeah.
Okay, so now let q be equal to z by 2. So this implies from here, it implies modulus q is less than 1. Is that fine? This quantity, because somehow I have to get something less than 1. Okay, somehow I have to bring it in this form, that something is less than 1. That something we'll put it as q. And the moment we get this q is less than 1, moment we have q is less than 1, then we immediately see that 1 by 1 minus q is equal to this one. Moment q is less than 1, 1 by 1 minus q is this. So therefore 1 by 1 minus q is equal to 1 plus q plus q square plus q cube and so on. Okay, so here of course, what is q? Q is z by 2. So 1 divided by 1 minus z by 2. 1 divided by 1 minus z by 2. What will this be equal to? It will be equal to 1 plus z by 2 plus z square by 4 plus z cube by 8 and so on. This is what we'll get. So this is an expansion, right? So can we get 1 by 1 minus z by 2? Can we somehow write it in this form? 1 by 1 minus z by 2. Can we do that? Think about it. Take maybe 1 or 2 minutes. Yeah, 2 common. If I take 2 common, or 1 by 2. Or what about minus half? If I take what if I take minus 1 by 2 common? If I take minus 1 by 2 common, then what will I get? If I take minus 1 by 2 common, numerator is 1, same, right? Denominator, what will happen? Check for yourself. Will I get this or not?
Yes, sir.
Okay, just convince yourself. Okay, this minus sign will become, when it goes here, this will become minus, this will become plus. So 2 into minus 1 is minus 2. and 2 into z by 2 is plus z, right? So we will get back this one, and this we already know. So this is equal to minus 1 by 2, minus 1 by 2, and this we already know. 1 by 1 minus z is basically this. 1 by 1 minus z by 2 is basically this. So that's a series expansion that right there. Okay, so you got one series expansion. All right, now let's look at the other series expansion. The other series expansion is 1 by z minus 1. Okay, this is the other series expansion. One by z minus 1, and this is what we need to find out now. So how do we go about doing this? Again, we rely on this one. Okay, the condition that we have. We rely on this condition. So how do we go about using this? Write down somewhere here. Okay, so this is what we have. So how do we use this condition now? In the previous case, what did we use? We used z less than 2. Here, what should we use? You can guess, right? What do we use? Which condition do we use? We'll use 1 less than z. Okay, this is the condition that we'll use. We'll use 1 less than z. Okay, now 1 less than z, 1 you take it on this side, z you bring it on this side. This less than is going to become greater than. Okay, this less than becomes greater than. This less than becomes greater than. All right, so then how do we get something like this? But what we wanted is less than 1, right? Here, what did we do? Just go back and just see here. We had z less than 2. All we had to do was divide by 2 and we got less than 1. But here we are having greater than 1. So how do you make it less than 1? How do you get a expression where we are having less than 1? Any ideas? How do you get something like here we wanted on the right hand side? On the right hand side, we wanted less than 1. Less than 1. And that's how we are able to obtain this because q must be less than 1. But here we are not having less than 1. We are having greater than 1. So how do we go about doing this? What should we do? Anyone? Is there any way by which we could, change this greater than into less than? Is there any way by which you can do that? This less than, if I greater than, if I can make it less than, is there any way? Anybody? Dishani, what do you think? How do we make this, turn this greater than into a less than sign? Dishani, can you hear me?
Sir, 1 by modular z.
Yes, the reciprocal. That's all. All you need to do is just take the reciprocal. Okay, so 1 divided by mod z. This will be less than 1. That's it. So we might as well go ahead and put the whole thing inside the modulus. So 1 by modulus of 1 by z is less than 1. Okay. So now what do we do this? What do we do here? So let, what is q? Whatever is inside this modulus. So q is equal to 1 by z. Okay. So therefore we will have 1 by 1 minus q. Can you just grab this from here? 1 by 1 minus q is this, which implies that 1 by 1 divided by 1 minus 1 by z. I'm taking this q as 1 by z. This is equal to 1 plus q is 1 by z, then 1 by z square, 1 by z cube, and so on. Is that clear? Now, how do we get this? 1 by 1 minus 1 by z. How do I get this over here? Somehow I need to get it in this way. 1 by 1 minus 1 by z. How do I get this? What if I take 1 by z common? What if I take 1 by z common? Then what will happen? So we will get 1 divided by denominator. What do we have? I have taken z common. So this one is going to be 1 minus, there is a 1 here, that 1 has to be divided by z. So this is what we wanted, right? And we got this. So this is equal to 1 by z, 1 by z, and then the summation we have already computed. We get this here. But we cannot stop here because we need to multiply this 1 by z. So that is easy, because if I take this 1 by z inside, 1 into 1 by z is 1 by z. 1 by z into 1 by z is 1 by z square. 1 by z square into 1 by z is 1 by z cube. 1 by z to the power 4, and so on. So this is what we have. So 1 by z minus 2 is this, and 1 by z minus 1 is this. So therefore this function, this original function f of z, the original function f of z was this. F of z was this. Therefore, the original function being this. So now we are in a position to just substitute. So we have, 1 by z minus 1, which is this. So 1 by z minus 1, sorry. 1 by z minus 1 is basically this. And 1 by z minus 2 is this one. One by z minus 2 is this, and this is this one. Okay, so now we can just go ahead and we can just open this up. So we will get over here, we'll get minus 1 by 2 minus 1 by 2 plus z by 4. Sorry, minus. This will be minus because this is a minus. Minus z by 4 minus z square by 8 minus z cube by 16 minus, and so on. And then we have, from here we have minus 1 by z minus 1 by z squared minus 1 by z cube minus 1 by z to the power 4, and of course minus, and so on. So we can write this in a form that looks like a Laurent series. So Laurent series, we always put negative powers first. Okay, so you can put the negative powers first. So dot dot dot. We have minus 1 by z squared minus 1 by z cube minus 1 by z to the power 4 z 1 by z cube 1 by z square minus 1 by z minus 1 by 2 minus z by 4 minus z square by 8 minus z cube by 16 and minus so on. So this is the Laurent series expansion. This is the required Laurent series. Okay, this is the required Laurent series. Is this clear? Now I have done this in a more very elaborate way so that you all are familiar with all the steps that I have used here. But yeah, but you can actually do this problem like within half a page. You can actually do this problem, provided you know what are the steps that you have to follow. Okay, so this was just the first problem. I would like to take a class with you all day after tomorrow. Would that be possible? Day after tomorrow. That is no day after tomorrow. Yeah, not day after tomorrow. Tomorrow. Would that be possible? Can I take a class tomorrow?
Yes, sir.
So what are the times that you all are free?
So we are free after 11 o'clock.
In the afternoon.